write it down. All right. Units?
Joules.
Yes. We're talking about energy here. This N is just a number. All right, so what it's claiming is that the energy has, because the orbits are fixed, the energy is actually fixed also. So if an electron goes from one orbit to the next, because it has it has to have enough energy to make the leap. If it doesn't have enough energy to make the leap, it's not going to go. Therefore, the electron is not going to spiral into the nucleus, because if it has a possibility of losing part of its energy, it's to get to the next level, it's not going to lose any. So, for example, an electron in the first orbit, so there's my nucleus. Sure. I have an electron right here. This is N is equal to 1. The energy it has of that orbit is 2.17 times 10 to the negative 18th joules, or if you prefer, plus some constant. The orbital radius is a sub 0, which we calculated last time.
5.303 times 10 to the negative 11 meters.
All right. In order to get to the next level, for the electron to jump up, well, the energy it would need is going to be, well, we got our base right here. Ooh, one small mistake. There should be a negative right there. The energy is negative.
Why?
If you want, pardon?
Why is the energy negative? Oh, there's
What is it a direction thing, or what is a negative energy?
Typically, when the potential energy is negative, when there's an attraction.
Okay.
We could make it artificially positive by setting where we want to bet potential energy equal to 0, but in traditional things orbiting have negative potential energy. All right, so that was with N is equal to 1. Now if we're at N is equal to 2,
Well, just plug and shove.
yeah, it's going to be that divided by 4. So that would be negative, what?
5.4257 times 10 to the negative 11. Not 10 to the negative 19.
Joules.
Joules.
So, which has a higher energy?
Well,
The first one.
the second one. The first one.
Is there a reason behind your saying the second one, or you just wanted to, you're reading my expression or something?
Well, it's gonna take a lot more to go to the second level than it is to just stay at the first level.
All right, so conceptually, do the numbers bear that out? That that's a higher energy level than that is?
Unless we just ignore the negative symbol, like the magnitude is higher. But
You're saying that magnitude's higher?
yeah,
Well, it's to the negative 19 instead of to
Yeah.
the negative 18. So technically, staying would be higher energy.
well, I said the first one because it's closer to 0.
Zero.
But I think it's not.
That's closer to 0.
Yeah, because there's an extra.
Yeah, this is, Ethan said, I heard him say magnitude. The energy is negative here, so we can't just dismiss the negative sign. This is a larger number than that is. Just as 0 is a larger number than negative 1. This is a larger number. So to get from there, so conceptually, in order to get to a higher energy, to a higher orbit, it needs energy, pumping energy into it, so this should have higher energy. So how much energy does it need to get from this level to that level? Well, just subtract. Negative 5.4257 times 10 to the negative 19th joules minus negative 2.17 times 10 to the negative 18th joules.
Yeah.
1.26. Yeah, negative 1.267 times 10.
It should not have been negative.
Oh, I just did the positive numbers minus. I did it backwards, I guess.
Okay.
I got 1.62772 times 10 to the negative 18.
Just the disagreement with the calculator exercise there. So you had 1.62 something, 627, and you had 1.2 something,
I had 1.627,
627. Okay.
which is basically what.
Okay. 1 point times 10 to the negative 18th joules. That is how much energy that is required. So what frequency of light would actually produce that? Well, frequency, I know that's the amount of energy. That energy hitting that electron is coming from some photon. So this would be the energy of a photon. So if we set that equal to the energy of a photon, which is h times f, the frequency of that light would be 1.627 times 10 to the negative 18th joules, divided by h 6.626 times 10 to the negative 34th kilogram meters squared per second.
What is H? Planck's constant?
Yes.
That's Planck's.
And yeah, so frequency is equal to the energy divided by h. And also a plot point in Stranger Things. Season 2.
What is the plot for?
What is the
I think it was a code that they needed, and somebody did Planck's constant. At that moment, I remembered the 6 at the front.
Okay, I got 2.456 times 10 to the 15th
Units?
hertz.
All right. So we have a light beam with that frequency coming in, hitting the electron, zips up to enough, that is just enough to get it to the higher orbit. Any energy less than that, or the frequency that is less than that, the electron does not have enough energy to make it to the next level.
So what we just found is the frequency of the light.
That the electron would have to absorb in order to move up. Now, if the light had a higher frequency, in other words, more energy than that, but not enough to take the electron up to 2 levels, the electron would take what it needs to get up to 1 level, and then leave the remaining energy for the light to go scattering off. Compton scattering. All right, so is this visible light or not? Is it probably not? Oh, let's find out. I know that the speed of light is equal to the frequency times the wavelength. The wavelength, therefore, is c over f. So this is 3 times 10 to the 8th divided by 2.456 times 10 to the 15th. That would be meters per second, and this would be hertz. And so what is the wavelength of this light?
And it's cool to use 3 times 10 to the 8th for our purposes today.
Yeah.
So the answer is 1.2 times, or 1.22 times 10 to the negative 7. Units?
It's radians per second? Radians per second?
No.
Is it just radians?
No.
Meters?
Yes. A hertz is a whatever seconds, so the seconds would cancel out up to meters. It's also wavelength, it's a length. So 122 nanometers. If that's not in the visible spectrum, it's pretty darn close. I just don't happen to have the visible spectrum right here. Actually, could somebody do a quick lookup of the visible spectrum? Wavelengths, the visible spectrum.
It's 380 to 740.
Okay.
I think this would be considered an ultraviolet light.
Okay. All right, so we're dealing with ultraviolet light that causes this. We would not see it, but we have detectors that can do that. If it went up to the next level, we would have more energy, but basically if you see the atomic spectrum, this is what's happening, is you shine light into an atom, the electrons get excited, move up to some level which is unstable. Then as they de-excite, they emit photons within visible wavelengths.
So shine light into an electron.
Shine light onto atoms.
Yeah.
The electrons absorb light, move up to higher energy levels if they can. It's unstable, the electrons collapse and send light out. And we can identify elements based upon that.
When you say put light onto atoms, is that like a flashlight or is it like energy?
It could be a flashlight.
So, but it takes a lot, right?
It depends. I mean, think of glow in the dark.
Mm-hmm.
You take ordinary light, you shine it onto the material, the electrons move to a higher orbit, but the time it takes for them to de-excite is longer, so it'll glow longer. So as they come down, they emit a light, which we see.
So so the light that we see comes from them de-excited?
Yes.
And is de-exciting the correct term?
It is a term that I have used for years.
De-escalating.
De-excited.
I've used it in front of physicists too, and no one has ridiculed me, so I'm going with that as the correct term.
All right.
What is the opposite of exciting?
De-excited.
The electrons get bored, move down to the... All right. This explains the atomic spectrum that we're seeing, that had been seen, because they had seen light shining on various materials or in various gases, and they see the light coming off of it. And so from that, they knew something was happening. They weren't quite sure what, but Bohr's model explains this. All right, so we now have some reasons for asking, are there any questions at this point?
Are we gonna get to like quarks and stuff like that?
Yeah, we will get to quarks get, yeah, that's well beyond
The scope of the course.
the scope of the course and the background for the most part.
Would we do that if we like a physics class in like later years of college, like a senior physics class? Or like
Yeah, I'm trying to think of the first time we actually, I mean, quarks have been mentioned at various points in the courses, but the first time we ever did a serious treatment of quarks probably was graduate level particle physics for me.
So, grad school?
Grad
Yeah,
school.
okay. That.
But I took a non-traditional route to physics grad school.
How do you mean?
I was a mechanical engineer undergraduate. Then I taught for a number of years.
Just let
Then I went and got my master's in physics and then taught for a number of years, and then went for my PhD.
You got bored with teaching, and then we went back to teaching after being taught for a while.
Yeah. Anyway. So we now have this idea that electrons are in certain orbits, light can behave like a wave, or light can behave like a particle, and it turns out it behaves like the way you're looking at it. If you're treating it as a particle, it's a particle. If you treat it like a wave, it's a wave. But a guy named Prince Louis de Broglie, or anglicized de Broglie, for his PhD dissertation, came up with this idea of, well, if light can be a particle and a wave, can an electron be a particle or a wave? Understand his dissertation was like 34 pages long.
Is it on Google?
You probably can find it in the original French.
What's the answer?
Pardon?
What's the answer? You said, could an electron be both? Is it?
Yeah,
It can?
it can, and it turns out. Now, we've been treating electrons like particles here, but this is the first time somebody puts in this crazy notion, and he ends up getting a Nobel Prize for it. The only person to get a Nobel Prize for his PhD dissertation. Now, the first evidence of his crazy notion was the Davison-Germer experiment. Two different people. Davison ends up getting a Nobel Prize. Germer does not. Make sure I spelled it right. The reason Germer doesn't is he was just the grad student, one of a string of grad students that Davison had. Davison had been trying to do this experiment for a while, and Germer just happened to be there when it worked. So what they decided to do is think of it as a wave. So if I send light, this is the double slit experiment, that if I send light towards two slits right there, and we talked about this the other day, that we end up with some sort of diffraction pattern. I'm off-centered, but the essence is there. So they decide to send electrons at a double slit. And as you send an electron towards the two slits, you would think that it's going to go through one or the other. So as they send it through, an electron would go through, and then you'd have some sort of material here, the electron hits it, it lights up, and you get a point. And then you do a whole bunch of it, and you get a point here, and a point here, and a point here, and some more points there, points like that.
Looks awfully similar to what we did for the wave.
Yes, it does. And if you do a histogram of it, you get most of them in this area. You get an area where there are no electrons hit, and then
Is that histogram, just the higher amounts in areas?
yeah. So you've got many more hits here than you do here, there, or there. If you send, so as you send one electron at a time, you get these points like this. Now it's a wave, but it only lights up a single point here, which seems odd. Then they decided to do a slightly different experiment. They put a detector here, and I think I mentioned this before, if not in this class, the other one. They put a detector to know which slit the electron goes through. So you send the electron through, and when you put the detector there, what happens is you get a whole bunch of hits here, and you get a whole bunch of hits here. You lose the diffraction pattern.
Huh.
So by the act of actually doing the measurement, you are assuming that it's going to go through one slit or the other. So you're now treating it like a particle, and it behaves like a particle. Over here, you were not using the detector. It didn't appear like a particle until it actually hit the board here, or hit whatever the backdrop was. And then it became a single particle again.
What? Well. So the English. So not having the detector there,
Right? It went through both slits.
it went through both slits.
Yes,
The existence of the detector
yes,
told the electron it's a particle,
yes,
and it acted as such.
yes,
Word.
yes. For some of you, it should be a little bit mind-blowing.
So,
So can.
so are electrons like, well, that's like, can like electrons think then?
No.
Why not? Cause like if they can sense things and they can operate to the
It's not because
existence of
it
other.
changed, it's because we were looking at it a different way, that we treated it as a particle. It's
Well,
always a particle, because.
No. It's
But it's
either a
acting
wave
like-
or a particle. It's not always one or the other.
But I can't think.
Well, not as we think, but I feel like it has some level of competence to where it can operate like this. This makes no
All right.
sense.
So, what's going on? Have you heard of Schrödinger's cat?
Yes.
Do you know the story?
No.
Put a cat in a box, and it almost died, it could have died.
Or did?
Or did.
Or did.
But it did both.
Yes. So you put a cat in a box, you have some radiation source that at some point it's gonna kick off the poison which would kill the cat.
Oh.
Now, the box is closed, you have no idea if the cat's dead or alive, and if you look, the cat will either be dead or alive. But if you don't look, the cat is dead and alive.
Obviously.
When you start dealing with this idea that things can be a particle or they can be a wave, how do you start describing it?
Is it based on the observer?
Yes, if there is an observer, but what I'm getting towards is when you start describing it, you create something which is known as a wave function. A wave function is a description of